All right, welcome back. Today, we're going to peel back all the layers and get right down to the bare metal. We're going to learn how to speak the computer's most fundamental language, and we're going to do it using something called bitwise logic.
I mean, really think about that for a second, because that's what this is all about. This isn't just about writing another line of code. It's about understanding how the machine actually thinks, how it processes everything at the most basic level possible.
Okay, so let's dive right in. Before we can start flipping bits around, we really need to get a handle on what they are. We're talking about the absolute building blocks of all digital data. You know, at the very, very bottom of it all, your photos, your apps, this explainer right here, it's all just a gigantic, massive sequence of ones and zeros. That's it. It's this incredibly simple system of on or off states that when you string enough of them together, creates all the amazing complexity we see every day.
This is honestly the best way to picture it. A single bit is just one light switch. It can be off, that's a 0, or it can be on, that's a 1. Every single piece of data on your computer is just a huge bank of these switches, all set in a very specific pattern. So if bits are the light switches, how do we actually, work with them? Well, that's where Bitwise operators come into play. Just think of these as our specialized toolkit for flipping those switches exactly how we want.
First up, let's talk about the AND operator. You'll see it as a single ampersand. This is probably one of the most common and useful tools in our entire Bitwise kit.
The rule for AND is super simple, but it's also very strict. For any given position, it will only give you a 1 if the bit from the first number is a 1 and the bit from the second number is also a 1. If either one of them is a 0, nope, the result is 0. And this truth table just lays it all out perfectly. You can see it right there. 0 and 0, you get a 0. 0 and 1, still 0. The only time we get a 1 is down there in that last row when both of our inputs are 1. And here's how it works with actual numbers, which is pretty cool. We just line up the binary for 9 and the binary for 5. Let's look at the rightmost column. 1 and 1. Yep, that gives us a 1. But for all the other columns, at least one of the bits is a 0. So the result is 0, 0, 0. And just like that, 9 and 5 becomes 1.
Okay, next up is a more inclusive operator. This is the OR operator, and it's represented by that vertical bar, sometimes called the pipe symbol. So where AND was really strict, OR is way more relaxed. It'll give you a 1 as the result if the first bit is a 1, or if the second bit is a 1, or even if they're both 1. See? Very inclusive. And you can see that clearly in its truth table. The only possible way to get a 0 with the OR operator is if both input bits are 0. In every single other case, if there's a 1 anywhere, the result is a 1. All right, now for a really interesting one. XOR. That stands for exclusive OR, and you'll see it as the little caret symbol. So the whole idea here is its exclusivity. XOR is all about checking if the bits are different. If one is a 0 and the other is a 1, you get a 1. But, and this is the important part, if the bits are the same, it doesn't matter if they're both 0s or both 1s, the result is always 0. And to round out our basic toolkit, we've got 3 more essential operators. First is NOT, which is the easiest one of all. It just inverts every single bit. It flips all the 1s to 0s and all the 0s to 1s. Simple. Then you have the shift operators. Left shift literally slides all the bits to the left, which is a mind-blowingly fast way to multiply a number by 2. And right shift does the opposite, sliding them to the right for a super fast way to divide by 2. Okay, so that's all the theory. But how does this stuff actually look when you're writing code? Let's jump into some Python and see how we can make these bits dance. So let's take a really common task, checking if a number is even. Now, most of us would probably reach for the modulo operator, right? But check this out. A much more direct and frankly clever way is to use the bitwise AND operator. So why does this work? Well, it's because in binary, only odd numbers have a 1 in that very last position. So when you do number and 1, all you're doing is checking that one last bit. If it's 0, the number has to be even. And why should you even care about this? One word, speed. The bitwise approach is lightning fast. It's a direct, low-level question you're asking the CPU, and it completely avoids the much slower process of mathematical division that modulo needs. For high-performance stuff, these little optimizations can make a huge difference. Now, this isn't just some academic exercise or a neat little programming trick. Bitwise operations are the absolute workhorses behind some of the most critical systems we use every single day. Seriously, you'll find them everywhere. In your operating system, they're used as little flags to control file permissions like read, write, execute. In graphics, they're used to tweak individual red, green, or blue color values. And they are all over networking, data compression, and especially in cryptography, where speed and precision at the bit level are absolutely critical. So look, if there are just two words to remember from all of this, they are speed and control. Bitwise operations give you amazing performance and the power to manipulate data with surgical precision, right down to that individual on or off light switch.
And that really brings us to the final question I want to leave you with. Now that you have a key to the computer's native language, what problems can you solve in a smarter way? What hidden performance boosts can you find in your own code? The power is right there at the bit level, just waiting for you to use it.